I told you that as we go through this chapter, we're going to make the graphing a little more complex each time. And what we're going to do in this lesson is we're going to add a c value. So if you look up here at the title, we have y equals ax squared plus c. So we're adding a constant. So let's see what that does to the graph. So in the first one, we've got y equals, or g of x equals, x squared minus 2. So that's just going to be very simply negative 2 squared minus 2, which is 4 minus 2. So that's 2. Why don't you pause the video and fill in the rest of the table on your own. All right, let's graph our points. Negative 2, 2. Negative 1, negative 1. 0, negative 2. 1, negative 1, and 2, 2. Make the U, extend it, label it. So now it wants us to compare it to our parent function, so let's just do that. It's got a chart underneath. We have f of x, then we're just squaring it, so that's 4, 1, 0, 1, 4. And now let's go and graph. Negative 2, 4. Negative 1, 1, 0, 0. 1, 1, and 2, 4. All right. Now, it might look like the graph of g of x is wider, but it's not. And we know that it's not wider because we know that fractional coefficients make graphs wider. So then you say, well, then what the heck happened? And what happened was that this graph, the black graph, just got shifted down too. I know it looks wider, but it's not. It's just this, the parent function, f of x, shifted down too. All right, let's do another one. So a little more complex. Now we do have a coefficient, so we know that it's going to change its width, and since it has a 4, we know it's going to get skinnier or narrower. So let's do the chart. We've got 4 times negative 2 squared plus 1. That's 4 times 4, so that's 17. So pause video and fill in the rest of the chart. All right, now then you might say, how am I going to fit this 17 on? And your grid might look different than mine, but what we're going to do is we're going to have our y-axis still down the middle, but we're going to have our x-axis all the way super down low down here. All right, so ignore my x-axis that's printed. You probably don't have one. So let's graph it. I've got negative 2, 17, negative 1, 5, 0, 1, 1, 5, and 2, 17. So that is super skinny. That coefficient really makes a difference. Holy cow. And now let's compare it to the graph of x squared. So let me put that on. I've got, it goes through 0, 0, then it goes through the 1s, and it goes through the 4s. Now, you don't need to show the graph if you know about the coefficient and the shifting, so drawing this red graph, f of x, on the grid was not necessary. What we're going to say, though, is that g of x is narrower. You don't have to say, like, how much narrower, just say narrower or skinnier, and shifted up 1. All right, so now what I'm going to ask you to do is I'm going to ask you to pause the video, and I just want you to graph this, okay? There's no chart, so you can make your own graph, but please just graph that f of x graph, and then I'll take it from there. All right, let's graph it. -2, 0, -1, 1.5, 0, 2, 1, 1.5, and 2, 0. Now we know it's facing downward because the coefficient was negative, and we know that it's a little wider than normal because it's a fractional coefficient. So that's f of x. Okay, now what they want us to do, get this, is take our f of x graph and shift it down 7. That's what this is saying right here. F of x, which is what we have, minus 7. So just take every point, shift it down 7. I'll add another column to the table if you want. So that's going to go to -7. That'll go to -5.5. That's going to go to -5. That's going to go to -5.5 and -7. So those are the y values, but really just visually bring every dot down 7 and then press play when you have the graph. All right, now what they want us to do in letter A is describe the transformation from F to G, which is what we did. Basically, it's what I told you to do. It shifted down 7. So G of X is shifted down 7. All right, great. I did that for you. Now what we have to do is we have to figure out what the equation would be of this graph. So if we're taking this graph, this f of x, and we're shifting it down 7, what would the new equation be? Well, it would be, the width didn't change, so it's still -0.5x, but the shift happened, so it ends up being -5 because it's the +2 graph, 7 down, so if you take 7 away from the +2 graph, you end up with -5. Now let's look at some terminology. That you're going to hear for all of your future work with quadratics. And the math word that I want to focus on right now is what's called a zero. And a zero of a function is an x value where f of x equals 0. We talked about these a little when we were solving our polynomials, right? So we called them solutions, and now we're calling them zeros. A zero of a function, when we're looking at a graph, is an x-intercept of the graph of the function. So when we have a graph, we're going to look for where it intersects the x-axis. So in example 4, we've got a picture of this building, and it tells us the function f of t equals -16t squared plus s sub 0 represents the approximate height in feet of a falling object t seconds after it is dropped from an initial height s0 in feet. An egg is dropped from a height of 64 feet. Well, first of all, that's very reckless. But this is a perfect example of the types of questions you're going to see in physics. These are real-life problems related to physics. So hopefully this doesn't make you hate physics. So what they're saying is that the initial height is s of 0. So really what they're saying in a roundabout way is that we're dealing with the function f of t equals -16t squared plus 64. So what we want to do is we want to figure out when it hits the ground. Now the height of the ground is 0. Hopefully that's not a surprise to you. The ground is 0 feet from the ground. So we need to figure out what the value of t is that makes the quadratic equal to 0. Now back in the polynomials chapter, we solved this using factoring. What we're going to do now, though, is we're going to look at where it hits the x-axis. So now when I go to graph, it doesn't make sense to be in any quadrant other than quadrant 1 because I'm talking about feet and time, so I can't have negative of either. So this is time, and the y-axis is feet. So now I need to figure out the points. So let's make a XY chart. So let me do 0, 1, 2, and 3. Okay, so I plug in 0. I get negative 16 times 0 squared plus 64, which is just 64. Why don't you pause the video and fill in the rest of my chart? So there's my table, and you can see I didn't even fill in the box for 3 because I knew that I couldn't graph it since I can't go below 0. So if I need to go to 64, I can go by 8s. I guess that's the best I can do. Okay. So that'll be 64. All right, so there's a dot right here at 0, 64. Then I have 148 and 2, 0. So now I just need you to understand this is not the path of the egg. This is the height at a particular time. Because this egg, if you look in this picture, is just going straight down. The egg isn't going to curve. It's just going to go straight down. But this graph represents where it would be at any given time. So how many seconds does it take to hit the ground? Well, it's hitting the ground at 2 seconds. Because that's where the x-intercept is. Last question, then we're going to wrap it up, is suppose the initial height is adjusted by k feet. How will this affect your answer in part A? Well, if k is less than 0, then it's going to take less time to hit the ground. So if k is less than 0, the egg will take less than 2 seconds. I'll use my fancy abbreviation. Less than 2 seconds. If k is greater than 0, the egg will take longer because it's higher up. All right, if you have any questions, write them down and ask me when you come to class.